Mm. Okay. So first, I want to give the motivation of why we want to study this prismatic displays. Let me start with a familiar example in characteristic zero in the global situation. In global situation, we have some geometric objects, for example, elliptic curves. Uh, these elliptic curves are given by some uh, linear algebraic gadget. Uh, Let me be more general. We have abelian varieties. These abelian varieties are equivalent to some linear algebraic package, Hodge structure of weight uh, 0 and 1. And they have a modular space, Ziegel modular variety. And so to every abelian variety, we can associate a uh, polarized Hodge structure with 0 and 1. And any such Hodge structure represent a point in the Siegel modular value. And the interaction between these different perspectives is very useful in uh, global Langlands stuff, in constructing Galois representation and proving modularity. So, uh, we want to understand this picture in mixed characteristic in the local situation. And the thing that we should consider instead of abelian varieties are Pfizer groups. Pfizer group is some kind of limit of uh, groups of order Pn when n goes to infinity. For example, you can get a Pfizer group by taking the limit of the Pn torsions of an abelian variety. Uh, and we have modular space of uh, Pfizer groups with fixed Newton polygon or fixed Hodge polygon, several stuff here. And we want to uh, understand the algebraic objects that are equivalent to these Pfizer groups. So we want to find some class of algebraic object, linear algebraic object, such that this map become an equivalence of categories. That's the first goal. Uh, so uh, if we want to classify the Pfizer groups over a perfect field by linear algebraic object, this is very classic. This is called P-Dune theory. To every Pfizer group over a perfect field, we can assign a projective module over W of K. We can assign a projective module over W of K. And for a Venus map from P to P, such that after inverting P, F becomes an isomorphism. And with an additional condition that, uh, uh, sorry, I have to add that this Frobenius is not linear, it's sigma linear. And it become an isomorphism after you inverting P and twisting the right hand side by for Venice. Uh, and with an additional condition that image of F should be contain P. This is the uh, picture over a perfect field, but unfortunately over general ring R, uh, we can't do this anymore. The D-Dune module is not enough to classify PDVL group. We need to put additional structure. So Zinc introduced the notion of display in uh, uh, 90. Uh, the idea is that uh, we somehow capture the divided Frobenius, the Frobenius divided by P. Display is quadrupel P, Q, F, and F1, such that P is over W of K, W of R is a projective module. Uh, Q is a submodule, such that Q uh, contains the Pershing-Munk multiplied by P. Uh, and we want that this exact sequence to be a split. Uh, we have P over IR in the middle, Q over IR, P over Q. We want this exact sequence to split. And F, as usual, should be a sigma linear morphism that become isomorphism after you invert P. And we want F1 to be divided for Venus. And morally, I don't write the exact equation, but morally F1 should behave like uh, Frobenius divided by P. And F1 is only defined over Q. F1 is a map from Q to P. Uh, so uh, why this is an additional data? Why F1 is an additional data? Because for a general ring R, W of R might have p torsion. If WR does not have a p torsion, then you can uniquely divide Frobenius by P whenever Frobenius is divisible by P. Frobenius of an element is divisible by P. But for a general ring R, W of R might have a p torsion. So you should make a choice for the divided Frobenius. And so you put this additional data, F1. So this is a display, and Zink himself proved that any formal p-divisible group over a reasonable ring R is given by such a display. There is an equivalence of category between uh, category of p-divisible group over reasonable ring R's and displays over such rings. And later on, Lau proved that this is always true for formal p-divisible group. Formal p-divisible group. There is a map to the category of displays, and this is an equivalent. Uh, this is a very good result. Displays are linear algebraic objects, and we can classify at least formal p-divisible groups by them. But the problem is that for a general ring R, W of R could be a very bad and complicated ring. It might have p torsion. It might be a huge ring. It might be a very bad. Uh, we don't we know little about the W of R for a general ring. So the question remains that can we can we find another characterization for this divisible group, more simple characterization. For example, if R is characteristic P, we can hope that A quiz of R uh, could be substitute for W of R. This is the theory of windows given by. And in some situation, you can do this. You can replace W of R by A quiz of R, which is usually a nicer, but not always. So this was a state of the thing until the 2015, where Scholz and Weinstein and Bott introduced new ideas to the field. So uh, let me first say that what we want to replace W of R. Uh, uh, if you look at the W of R, it has an important ideal that appear in the definition of display. It's Pershing. Uh, it has a distinguished element, P, which also appear because F1 is Frobenius divided by P. And it has of course, a Frobenius on it, sigma. And it has a divided Frobenius. If you like, you can write it Pershing. This is the gadget that we define the display on, the theory of displays. Uh, we want to replace these gadgets with nicer things and more general things. And this is what happens in the theory of prismatic cohomology. A
Uh, uh,
prism,
Ali, sorry, can I ask you a question?
yes, yes, yes,
So I missed the definition, sorry, but this WR, is it like the bit vectors or
yes,
R?
exactly. It's a bit vector.
Okay, okay,
This
good.
bit
Thank you.
vector, version P, Frobenius, and
Okay,
yeah,
thank
we can
you.
classify physical group by displays over these gadgets, but the problem is that W of R could be very complicated. We want a more simple. So we want to replace this by a better choice. Uh, this is done by Bott and Schulze in the theory of prismatic cohomology. Uh, a prism, let me recall the definition of a prism. A prism is a ring A with a Frobenius, more precisely a delta structure, but I don't want to go into that details. So a prism is a ring, a Frobenius on that ring, a Cartier divisor I, uh, such that uh, P is in idea generated by I and sigma. For example, in this case, P is in sigma of itself. So we call such a thing a prism. Of course, it should be A should be uh, POI count. An example. Let me give a few example of important prism. For example, if R is reduced, then the value of R, sigma, and P uh, is a prism. R should be reduced because otherwise WR might have P torsion and this would not be a Cartier device. Another important example comes from p-adic H theory. I shown that C is a CP is algebraic closure of completion of algebraic closure of QP. In p-adic H theory, they define a ring A inf of CP. And this is defined by taking the first we take uh, O of CP modulo P, then we take the perfect per- perfectly divided, take the inverse limit over Frobenius. This becomes something we call tilt of that uh, ring. And then A int defined to be the width vector of this. This is an important thing in the periodic hash theory. And there is a natural map from uh, A inf of C, CP to CP. And it's kernel generated by uh, a single element which is non-zero divisor. And uh, this is an example of a prism. A inf of CP, uh, natural Frobenius on it, and this uh, kernel. This map called theta is your kernel. And morally, this is the prism that classify the PDDL groups over OCP or CP. Uh, yeah, which
Sorry, can I ask a question?
yes.
Can I just clarify? What do you mean by CP again? Is it completion, periodic completion?
You take QP, you first consider the algebraic closure, and then yes, you PID completely. It becomes
Uh-huh. Okay.
yes.
Thank you.
And
Thanks.
okay. So this is the prism that give us information about PDDL groups over C. Another important example is when you have a finite extension of QP, for example, E over QP. This you can decompose this as a unramified extension uh, and a totally ramified extension. This is that. And this extension is given by a Eisenstein polynomial. Sorry. W of alpha, W k of alpha, where alpha is the root of some Eisenstein polynomial D of. Uh, uh, it's a natural question to talk about the p-divisor groups over E or OE. And the prism that you should care in this situation is the prism given by Kissin again in p-adic hash. So let me recall the definition. Uh, you have this ring W of K, double bracket U. You can naturally define a Frobenius on it by sending U to UP. You can consider the idea generated by E of U as the Cartier divisor. This is a prism called the Kissin prism, and as I said, it's a prism that is associated to O. Let me be more precise. What I mean by that, a prism associated to a ring. A prism is basically, if you forget the Frobenius, a pair of A and A. You can take the quotient, and morally, this prism is give us information about the pixel groups over this quotient. Uh, this is the general idea. If I want to be a little more precise, if you have a ring R, you can define a site over it, prismatic site over R. This consists of prisms A and I, such that A over I is an alleged. And you can consider this site with étale topology or whatever topology you want. I think the étale topology is the right one for that. You can work with flat topology, étale topology, whatever. So you can consider this site over. A natural question is when this site has a final object. Uh, this There is a special class of rings called quasi-regular semi-perfectoid ring. For this kind of object, QRSP, for this kind of object, this site has a final object. If R is QRSP, R delta has a final object, which we show by delta of R. For example, if uh, R tilde is a perfect ring characteristic P, and you divide it by a regular sequence, this is an example of what we call quasi-regular semi-perfectoid. And in this case, delta of R is just a cubist of R from P education. But you can have a similar situation in mixed characteristic. If R is a perfectoid, and you divide it by a regular sequence, you get an example of quasi-regular semi-perfectoid ring, and the upshot is that the prismatic site of R has a final object delta R, which would be a substitute for the width vector of R. This is usually a much nicer. And
Sorry,
so yes.
just one quick question. By Chris, you mean like a? Do you mean like a stack?
Sorry, what? By
Um,
Chris? Yes,
Earlier on when you wrote Chris, yeah.
I wrote the definition. A prism is a ring a Cartier divisor I, and for venues from A to A, such a data is called a prism. A prism over R is such a data such that A over I is an R algebra. And the prismatic side over R is the set of all these prism over R with the whatever topology you want. And as I said, for quasi-regular semi-perfectoid object, it has a final. There is a bigger class of ring called quasi-symptomic rings. These quasi-symptomics are a generalization of locally intersection rings. For Noetherian rings, quasi-symptomic rings are exactly local intersection rings. But this is a generalization to non-Noetherian situation. These are the rings such that the cotangent complex of L over ZP has weights in the interval. And the good property of quasi-symptomic rings is that for any quasi-symptomic ring R, you can find a faithfully flat cover S such that S would be quasi-regular semi-perfectoid. So by the method of descent, we can translate the information we have about quasi-regular semi-perfectoids to a general quasi-symptomic ring. And these are a very, very big class of ring. You get every local index. And so we want to define a display over this quasi-regular semi-perfectoid ring, which we call prismatic display. First, we define it over quasi-regular semi-perfectoid, and then by descent, we extend it to any quasi. So what do we mean by a prismatic display? A prismatic higher display is the data of uh, uh, projective a prismatic higher display over R is a projective module over delta of R. We are assuming that R is quasi-regular semi-perfectoid. So there is a canonical piece associated to R, the final object of the prismatic set of R. So a prismatic higher display is a projective module over W delta of R. A decomposition for P into uh, projective submodules. A series of maps Fi from Li to P. This should be morally the divided Frobenius. This is Frobenius divided by Di, where I shown that the uh, delta of for quasi-regular semi-perfectoids, the ideal we have in the definition of prism is always principal. So D is the generator of the ideal of the prism we have in the definition. So we have this series. We should have this series of maps which are divided Frobeniuses, and we want we can decompose these maps to a single map, div of f from P to P. This is a map that over Li, you can, I mean, you can write P as the sum of Li, and you have this map Fi from Li to P, and you can combine this to get a divisor. We want this to be isomorphism. Again, after the linearization. So this is a display, prismatic display, what we call a prismatic display. And once we have the prismatic display over a quasi-regular semi-perfectoid ring, we can define a prismatic display over a general quasi-symptomic ring by the method of descent. The idea is that prismatic higher display over quasi-symptomic ring R, if you want to define it, first you should find the quasi-regular semi-perfectoid cover, and then you have the fiber product. You should find the quasi-regular semi-perfectoid cover for this one also, and then prismatic higher display over R is prismatic display over S, such that the image of the prismatic display under these two maps become the same. It's exactly what it should be, so that it becomes a stack. The category of prismatic higher display becomes. So this is our definition of a prismatic higher display over quasi-symptomic ring. And the important property is that there is a work of Anschutz and Lebra that they give a classification for p-divisor groups over quasi-symptomic rings. In our language, the result of Anschutz of Lebra tells us that a p-divisor group over a quasi-symptomic ring R is equivalent to having a prismatic display over R. So prismatic displays are the right algebraic edges. They classify it. The next natural step is to define a group theoretic version of this linear algebraic objects, because we want to talk about the point of a local Shimura variety. And to do this, we should have a group theoretic version. Let me say what I mean by the group theoretic. For example, we want to talk about p-divisor group with additional structure, with a quadratic form. In that case, we should have a notion of SO2 display. SON is to talk about the p-divisor groups with quadratic form. how we do this? Let's first do the case of ordinary displays that are supposed to be GLN displays. To give a GLN display, what data you should give me? At least the simple one. To give a GLN display, one if you assume that the projective module is free, then you should give a filtration by uh, uh, submodules. Let me fix the co-character so that I let me fix this filtration by fixing a co-character. Uh, the only other data I should give you is this divided Frobenius that I have had in the definition. This is just a matrix. So to give a GLN display, I should give you an element in GLN of delta alpha. But two different matrices could give us equivalent display because one can change the bases. So I should understand the effect of change of the basis on this matrix U. The point is that not every change of basis is uh, uh, okay because sorry, uh, I have this filtration. I have these limits are my choice of change of base. Uh, the good choice of bases. Let me give an example in GL2. In let F to be delta R power 2. And let me give a decomposition E1, a basis as E1 in E2. And let's assume that F of E1 is divisible by D is something. And F of E2 is not divisible by D. So this would be my F1. This would be my E2. And I have a divided Frobenius from E1 to F, which sends X to, I have too many Fs. Let me change the two. Yeah. Sorry. This sends X to Frobenius of X divided by D. It is divisible by D because of this assumption. So uh, let's have a matrix here. Assume that f of f assume that f1 of E1 become a E1 plus b E2. So f of E1 is d times this, and f of E2 is c E2 plus c E1 plus d E2. I can consider these matrices. Uh, if I want to give a change of basis, uh, I should choose another basis instead of EX such that this property still holds. I want if I want to take another basis, I want f of f1 to be still divisible by d. For this to hold, f1 should be of an special form. It could be a multiple of E1, but on the if I want to f of f1 to be divisible by d, uh, the multiple of E1 could be arbitrary, but for E2, it should be divisible by d because f of E2 is not divisible by d. So divisibility should come from the coefficient. And F2 could be anything. So uh, matrices that I could change coordinate by them has this special form. They are at the form x, y, t, sorry, x, z, t, dy. One component should be divisible by it. And in general, there is a similar situation. We should have for the change of coordinates matrices, we should have a condition on divisibility of some uh, some of the uh, elements of the matrix, and it goes like this. We have a so I had fixed the co-character if you recall. I want to define the right change of coordinates, the right group of change of coordinates. This is defined to be the kernel from sorry we have a ring p nu of a over r and let me organize my code. Let me define it this way. Assume that G is a spec of S. This mu gives a filtration on S. Over here we have delta of R. It also has a natural filtration where called Nygaard filtration when Ni of delta of R is Frobenius inverse of di. So I have two filter rings. An element of the sheaf of group G mu of R is defined to be a map from S to delta R that respect the filtration on both sides. So G mu of R is the set of these maps, and it has a natural group structure. This is a subgroup of G of R. As I said, these are eligible change of coordinates. And Banal display over R the category. Uh, this has as objects uh, elements of G of delta R, which morally are my divided Frobenius. As morphism, it has element of G mu of R, which are my change of coordinates. And how this morphism works, if I have a K over here, K gives me a morphism from U to this thing. Mu of D, sigma of K, mu of D inverse. If you are familiar with the isocrystal, this Frobenius here should not be strange. And this conjugation, but by mu is because we are not considering Frobenius, we are considering divided Frobenius. So this mu appear in the formula. So this is the stack of Banal display. Sorry, Perez stack of Banal display. These are the objects, these are the morphisms, and morphisms are like this. And but this is not a stack. We should stackify it. We should take the objects we are getting by descent to get a stack of displays overall. So I define the pre-stack. You can uh, associate a natural stack. It's the G mu. Well, this is the group theoretic version of the notion of display. Uh, and we have a conjecture in our paper that an element of this stack over R, like we write this stack by DG. And we could also add a B over here. This means that our display modulo P is isogen to the display defined by B. I don't go to detail, but it's a slight modification of this stack of display. We had a conjecture in our paper that an element of this stack is having an element of this stack is the same as having a point R point of a local Shimura variety. In fact, we have a map like this, and this is an equivalence in the Hodge type situation. We can prove this if G is, for example, GLN. This is the equivalence of category. And in general, we know that it's a equivalence of category over algebraic closed field. And we can also reduce the equivalence of this map to the question of representability of if, for example, if this integral Shimura variety is representable, then we can prove that this is an equivalence. So we have a strong evidence that this map is an equivalence. So upshot is that the points of integral, the point of local Shimura varieties are complicated things in general. So we are by this equivalence, we are giving a linear algebraic description of the points of our integral Shimura variety. So this is a conjecture, but there are very strong evidence that this should be true. As I said, it's true in the hashtag because we have representability for that situation. So these are the objects that we want to study, and they are important because they are related to the local Shimura varieties, and local Shimura varieties are important in the Langlands program. A natural question that arises is to study the deformation of these objects. If we have a thickening, an nilpotent thickening of quasi-symptomic rings. For now, I shown that both of these are quasi-symptomic. We want to understand the meaning of lifting a point in dg mu of R to dg mu of we want to understand the lift. If is there any lift for X, what we can say about the different lifts and so on. So the question of deformation of this object. For a very general class of quasi-symptomic rings, not for all of them, but for a class of nice quasi-symptomic ring, we can exactly describe this deformation. Let me tell you how. It's our description is very similar to Gerotin messing, if you heard of it, in the classic theory of Philip So, as I said, an element of Eg mu R it's something like one can also look at it's a G mu torso for the group G mu I defined earlier. Uh, it's a G mu torso. Uh, there. I have two map from G mu to G. One is the inclusion, and one is this where map appeared in the formula previously. And uh, an element of P G mu of R is the data of a G mu tensor L, and an identification because between the uh, pullback of L under these two different. Let me give it a name. This is another description for a prismatic display. And did this is over delta of R, not over R itself. This thing. And one important property of this group G mu is that if you uh, mod out this by D, you get the ordinary parabolic subgroup associated to you. So if you consider G mu mod out by D, you get P mu. So I can, if I have a if I have a prismatic display, I can mod out by this element D, delta of R modulo D just becomes R, and uh, this L I have this G mu torso give me a P mu torso. And so to every display I can associate, the option is that to every display G mu display I can associate the P mu torso. And so the theorem we proved is that to lifting a display X to from R prime to R, it is equivalent to lift the associated P mu tensor from R prime to R. This is as I said, like the Garrett-Hindley message situation. For example, if G is GLN, if G is equal to GLN, a P mu tensor is just a filtered vector space. And to lift the GLN mu display from R prime to R, you should lift this filtration. This is the Garrett-Hindley messing theorem that if you want to lift the p-divisor group from R to R prime, you should lift it Hodge filtration. So it's a reaffirmation of that. So this is the main result in our paper. And we could go a little further. Let me mention this. Uh, uh, up until now, we only talked about the quasi-symptomic rings, but there are natural rings that are not quasi-symptomic but are related to quasi-symptomic. For example, consider this situation. Let me give an example in characteristic. Consider this ring. This is an example of a quasi-regular semi-perfect rings. We have a perfect ring divided by a regular sequence. We can consider a thickening of this ring. When you consider the ideal difference. This is a thickening, but this is not quasi-symptomic because this ideal is not generated by a regular sequence. It's generated by 2 y2 xy. It's not a regular sequence because if you, this is a zero divisor in this portion. And one can hope that by the method of deformation, we have a good understanding of PDZ group over this ring because it's quasi-regular and perfectoid, and we have the theorem of Anschutz and Lepra that says that says to us that a PDZ group over R prime is just a prismatic display over R. One can hope that by the method of deformation, we can understand the PDZ group over R as well. And this is the case for a large class of thickenings of the quasi-symptomic rings, which themselves should not necessarily be quasi-symptomic. We can classify the PDZ groups over these rings by some linear algebraic objects, by some version of this prismatic display. This is a new result because in the paper of Anschutz and Lebras, they only talk about quasi-symptomic rings. Here in our paper, we can extend this result a little bit to nice thickening of quasi-symptomic rings, thickenings that look like this. We have a situation like this. You have a perfectoid divided by an ideal I. You can classify PDZ groups over a perfectoid divided by an ideal I2 or IN. So this is a nice result. A natural question is that how far we can extend this classification. For example, we only can prove it for some nice thickenings. Can we prove it for every nilpotent thickening of a quasi-regular same perfectoid ring? And question 2 is that can we prove the conjecture I showed above without the representability? Because proving the representability of local Shimura variety is very hard for outside of Hashtype case. And we prove that if the local Shimura variety is representable, then the map I had is an equivalence. But if we can find some other way to prove this equivalence, maybe we can use this equivalence to prove the representability of the local Shimura variety. So if we know the representability, this is an equivalence, but representability is hard. Another natural question is if we can prove this conjecture without using representability. Yes. These are two natural questions that we want to consider. I think my time is over. Is there any question?
I've got one question. Do you get anything nice when R is like a simplicial commutative ring?
Simplicial. I think you can generalize all the definition to simplicial things. In fact, there is a work of Lori and Bott. They
Animated.
Yeah, they define a stack called Cartier with a stack. This stack is not only defined for ordinary ring but for any simplicial. And vector bundles on this stack are closely related to what we define as prismatic displays. So you can define this stack for simplicial things, so you can consider the vector bundles over them, and you have some version of prismatic displays over simplicial.
Sure, some Khan complex or something like this.
Yes.
Interesting. Thanks.
I think Ismail also has a question.
Okay, any other questions?
Yeah, I have one question. So
Go ahead.
I'm wondering if your theory would help or provide some method for producing local model for Rappaport zinc spaces. Just asking like myself, would it provide some sort of approach for doing that?
I think at least in the Hashtype case, there are some work of Kato that he uses this some version of this prismatic displays to prove that the local model of Hodge type local Shimura varieties are smooth. So it certainly could give us some information, but for constructing local models, I don't know. It might take time.
Mhm. Okay. Okay, thank you.
Guys, other questions? If there's no other question, let's thank Ali.
Thank you.
All right, so we meet again in 2 weeks.
I think the next meeting will be on Thursday, I believe, right? I have to check. Not
All right.
Tuesday, but Thursday, I think.
Oh, so that's the